Panel discussion session for today. We're going to discuss the science case or cases for joint observations of LSST and LIGO. So, what's really the science that we can address with joint observations versus individual observations with LSST or LIGO alone? And as usual, we have a couple of panelists here who are going to present some ideas that we're going to discuss. I guess we have like half an hour.
Yeah.
So we, as I guess, started. Do you have the slides up there?
So I have
who's going to
start?
start?
What's the name of the slide that I should look for?
This slide?
Yeah, which one?
I have no transcript.
This one?
Yeah.
This is one for codes, but can you send the other slides as well?
Yeah, I think so. I send you slides myself. Should we get?
Yeah, this one. I get it.
Should we get 47 first?
I get it.
What do you want to start?
I think it's better to probably talk after the your talk.
After mine?
Yeah.
Okay.
You're right.
All right. Should I? Okay. Then I'll just.
Because I think I'm talking about more with radio, not summer stuff. Right?
Okay.
You're probably talking about to some radio stuff.
Yes. Sounds good. Okay. So I'm gonna start, and I just wanted to come back again to this question of the origin of short Gamma bursts that also Satya has mentioned in his talk already. So. At least from first principle calculations, we still don't really understand how short gamma bursts are produced in neutron star mergers. We do have some indications, at least in the case in which we promptly form a black hole after merger. So there are MHD numerical relativity simulations who indicate that there's a funnel forming and that at least the necessary conditions to launch a relativistic jet are sort of met. But in the case in which we form a long-lived neutron star in such a merger, we still don't really understand on first principles how such a jet can actually be produced or launched. And so this is essentially nicely summarized in this graph. So these are recent simulations that we did in which we collided neutron stars. And in one case, so we chose different equations of state. In one case, we chose an equation of state with a low maximum neutron star mass, and that promptly formed a black hole after merger. And so once this black hole forms, the pressure support essentially stops, and material with low angular momentum in the polar funnel simply accretes onto the black hole and evacuates this sort of polar funnel in which you can at least have some low density region, low baryon pollution, so that you can actually have at least the necessary conditions to launch a relativistic jet. Whereas in the other case, where you form this long-lived neutron star, you have this isotropic baryon pollution that I was also mentioning earlier today. And at least for over the lifetime of this simulation, we don't really see that there's any sort of polar funnel clearing up that could actually produce a baryon poor region for a jet. So there's some problems with trying to understand how short gamma bursts can be produced. There's several ways out of this. One scenario that we proposed a couple of years ago is that maybe this short gamma burst is actually produced much later, not at the time of not at the time of merger, but is rather produced when this long-lived neutron star collapses to a black hole, and that might be after a spin-down timescale, which for typical parameters could be minutes, hours, or maybe even up to days. So my point that I just wanted to make here is that we're not really sure yet when and how short gamma bursts are produced in these mergers, and doing joint observations on the electromagnetic and the gravitational wave side might actually give us some indications and might constrain different theoretical ideas on how short gamma bursts can be produced in neutron star mergers. Simply because scenarios like this have very distinct electromagnetic signatures that we can look for and that we can test, and then once we have observations, we can actually constrain those models. One specific prediction of this model, for example, is that there might actually be some precursor electromagnetic emission prior to the short gamma burst. So where and how this electromagnetic emission manifests itself is still a matter of debate, and we have to come up with better theoretical models for this. But there could be actually a optical or UV precursor, maybe in some cases even an X-ray precursor to the short gamma burst that we might be able to look for with joint observations of LSST and LIGO in the near future, trying to understand better how short gamma bursts can be produced.
But you're talking about minutes or hours or days?
Yeah, that's a very good question.
I mean,
so,
for LSST, if it's minutes, you probably are not looking at the right place at the right time. So,
right. Well, minutes would be like sort of an extreme case probably. So at least in this scenario where the neutron star has a spin-down time scale to collapse and produce the GRB, it's more on the order of like hours, maybe even up to a day, depending on how strong the magnetic field, for example, is that this neutron star is born with. But these are parameters that we don't exactly know. So there's some uncertainty to this, but typically it could be on the order of hours to days, and so there could be some sort of precursor signal that we might be looking for.
Do you have a chance, so, where if you detect the GRB/gravitational wave, order 5 years, that's not going to be sooner most likely, right? Is there any other way you can test this before that on a shorter time frame, just from electromagnetic, for example?
Well, so it depends a little bit on the exact emission that we're looking for. So it's something that we still need to determine better on theoretical grounds. So where the signal is actually really going to peak and how bright it will be. It could be that there's significant X-ray radiation at the early stages or so. We might be looking at these things with X-ray satellites or so, existing facilities. But it's very hard to catch. So the possibilities are very limited. So. The exact timing will be very interesting and will be most constraining. So the gamma rays and the gravitational wave signal, and then hopefully something in between or after that.
So what kind of spectrum do you predict for this precursor?
So there's different. So Kota will probably also talk about this a little bit after me. So there's different. So there's thermal and non-thermal radiation. I would predict a strong thermal component, and when I'm talking about optical UV, it's probably mostly thermal radiation. So energy that is extracted essentially from the central engine, from this neutron star, that is reprocessed by this nebula, is sort of reabsorbed by this outer ejector layer. So this is where the energy essentially becomes thermalized, and this is what essentially provides the thermal spectrum. But then there might be also other types of radiation that is probably higher energies, at higher energies, X-rays or gamma rays might be able to escape because simply the opacities are much lower in those wavelengths. So there might be other non-thermal signals that we might see as well.
But your X-rays will not be kind of...
Yeah. Well, so if this ejector can be actually really heated up to fairly high temperatures, then you can touch like the soft X-rays or so probably, but it still needs to be better understood.
What is the process that transfer the energy from pushing the ejector to thermal energy? What's the mechanism? I mean, I understand if you push something, you give it kinetic energy, but then you have to transfer the kinetic to get radiation. You have to transfer the kinetic energy to thermal energy. Particularly, you're talking about thermal energy. How do you thermalize the kinetic energy?
So in this case, it's not really thermalization of just kinetic energy, but actually what is heating up the ejector and what is, say, thermalizing energy in this ejector layer is this pulsar wind nebula. So what is actually happening is that you have this neutron star, this fast rotating neutron star that via the pulsar wind feeds, so it extracts rotation energy into this pulsar wind.
Pointing flux.
Yeah.
So how do you convert the pointing flux to thermal energy? It's even more difficult.
Okay, well this is like the general problem of pulsar wind nebulae, right? So like
there is a completely different story. There you convert it at very large distances, and you're accelerating particles, and it's a completely different story. Here you want to convert directly pointing flux to thermal energy, and I don't know of a mechanism that does it. So,
well, we're sort of hypothesizing that a pulsar wind nebula like the conventional pulsar wind nebula that we know of, are sort of generated in this system just on different time and length scales, so that you have essentially something like, I don't know, a termination shot in which you thermalize the Poynting flux into particle energies.
But not summer, right? So the usual pulsar wind nebula, basically the most of the Poynting flux is converted to non-summer particles.
Yes.
Particles.
Yes. So and then you have like as in a usual pulsar wind nebula, you have heated up particles that undergo high energy.
And emission in the pulsar is the classical pulsar wind nebula. That is not the classical pulsar wind nebula. This is just the explosion, right, that you're talking about.
This is not an explosion. This is just the ejector material that is ejected during and after the merger on timescales of say tens of milliseconds up to a second or so. That is moving away from the got unbound like during this process, and that is moving away from this merger site. And it's just confining this pulsar wind
So
nebula.
how long does it take to go from here to there to there? I mean, it's not like thousands of years. It's just seconds,
Yes.
right?
Well, it's so this is on the this whole thing is on the timescale of spin down timescales. So this is from say the shortest is probably like on the order of minutes, and then you go to hours and days.
I mean, I don't think we know how well it thermalizes, but one way you
Yes.
can thermalize it, if you create this nebula, which I agree, you have to have some reconnection or some sort of, trap the magnetic field, it undergoes reconnection, you accelerate non-thermal particles, you non-thermal radiation, and then non-thermal radiation can be absorbed by this
Right.
ejecta, if it's UV or soft X-rays, by bound-free processes, and then that re-emits it as thermal radiation. So there are ways, but it depends on where exactly this nebula is putting its energy. If it's putting it at really high energies, it's just going to leak out.
Right.
And so you have the presumption is that some fraction of it will be in an energy range where the ejector can absorb it and turn it into something thermal. But there may also be a non-thermal component in this.
Which is better for you, if it's thermal or non-thermal for observation purposes?
Well, that exactly depends on how these signals would exactly look like, and
If it's thermalized, it's likely to come out in the optical, like the
yeah.
filament or infrared.
Or
If it's
UV
non-thermal,
or
it can be harder X-rays or gamma rays. I'm going to guess the hard gamma rays are going to be hard to detect with these luminosity.
Okay.
Depends on whether you have an X-ray satellite or.
So you would prefer optical?
So it's but I think no summer is sometimes better, right? Because if you want summer that you have degeneracy, right? You can may not be pulsar or summer. The energy source can be different, right? Some energy source output might be produced by some different energy, right? If you see the X-ray, the no summer particles, and then maybe you can directly see some internal dispersion.
Sure, in terms of what you learn from it, maybe you learn from it.
So it's not out of the question that this could be like a hard X-ray precursor that you could see with that before the short GRB itself.
I don't know at this stage. Probably you can rule it out. Yeah.
I guess I'd like to know more about the model for the delayed gamma ray emission. Because I mean, right now on LIGO, I think we're only searching out for like 6 seconds or something.
Right.
1 second, right? We searched 6 seconds before.
Oh, right, yeah, I had it backwards.
So one before and 5 after, right? Or-
No, I
No,
think
5
everybody
before.
said it's the other
Five
way,
before
right?
and one.
Yeah,
Are you
so
sure?
for the precursor, so if you have the gamma ray burst, search for 5 seconds before the gamma ray burst and 1 second afterwards,
Okay.
I think. Because,
Right.
yeah, so this is the opposite. So we are really, the applicable number is 1 second.
At any rate, it's still way
Yeah.
smaller than minutes or days or hours or
Right.
weeks or whatever. So, I realize, I mean, I guess it sounds like a lot of the problem was saying whether or not it's, okay, so a second wouldn't be bad, it would still kind of fit.
Sure.
A minute would be bad, an hour would be bad. Like, part of it would have to do with like what the time to collapse is, and I realize we don't understand that very well,
Right.
but you must be able to put some prior expectation. Is it more likely to be minutes, or is it more likely to be days, or it can't be uniform, can it?
No.
That would suck.
Yeah, that's a good point. So these short delays are typically expected if you form a what you call a hypermassive neutron star. So and that very much depends on the equation set that we also don't understand. So if you form these short delay times would apply to hypermassive neutron stars or prompt black hole formation, and they would be typically on the timescales of milliseconds, tens of milliseconds, maybe hundreds of milliseconds. So definitely within this window. So these hypermassive neutron star collapses, they should be sort of captured by the usual search window.
Okay.
The problem, I think, is that once you really form a long-lived neutron star, by which I mean like a supermassive neutron star, so that can still be sustained, so that in which the gravitational collapse can still be sustained by solid body rotation to some extent, and so this will spin down via its magnetic field until it has lost like a significant fraction of its rotational energy, and that sets the point of the time of collapse. So now the spin down time scale, so this time scale over which it loses a significant fraction of its rotational energy, depends on the magnetic field via which it spins down. So and this magnetic field is essentially produced during the neutron star merger by a magnetohydrodynamic processes. So there's a lot of magnetic field amplification. And we are studying this in simulations, but there's still no consensus, or there's no definite conclusion on what a typical magnetic field strength and topology of the magnetic field after the merger is. So various groups are investigating this. We have some ideas about the magnetic field strength, which is probably on the order of typically 10 to the 15, maybe up to 10 to the 16 Gauss. And so over this range of, say, possible magnetic field strength, if I just plug this into some spin-down formula that predicts this lifetime of the neutron star, this is essentially what then tells us that this has to be somewhat between, say, minutes, a few minutes, and maybe up to days.
The gravitational wave emission, I mean, if it keeps any kind of time-varying quadrupole movement, it'll keep radiating gravitationally too. And I realize that, like with normal pulsars, we say, oh, well, the magnetic is going to be so much more. In fact, we place limits on crab pulsars and things like that in terms of spin down. But for this thing, like, it's going to be a weird thing. Like, I mean, it's going to have all kinds of weird modes. It might radiate a lot gravitationally for a while, and that might actually dominate the magnetic, right?
Yeah, it might. So that is typically what drives the whole thing to a more like axisymmetric state. So this is like between for the first tens of milliseconds or so. This is where gravitational wave emission probably through the oscillation mode is probably strong, very strong, and sort of drives the object to a more axisymmetric state. But once it's in this axisymmetric state, gravitational wave emission will essentially cease, and then the spin down actually takes over, and this can then take over for a spin-down timescale, meaning for up to days. Yeah.
But then I just move on because
sure. We can. Yeah.
Very briefly, if the internal field is 100 times stronger than the external dipole field and it's misaligned, it will spin down faster because of that distortion from gravitational waves than from electromagnetic. But it does have to be. We have to have a much stronger internal field to like sort of change the shape of the star. That's not modes. That's just like just a non-spherical distortion.
This depends on which kind of gravitation.
Yes, there's different. Our modes are not that much.
Can I ask one more question on this topic? So you said that in this time reversal scenario that the short GRB would emerge when the neutron star collapses to form a black hole. What I missed is what actually happens during that collapse that causes the short GRB.
Okay. Yeah, very good point. So I'm looking at Ben. Ben is laughing. So this is what I was not mentioning. So of course these alternative scenarios, they don't come without problems. I mean, they also have their own problems, and especially this one also has a problem, namely that we sort of assume that during this collapse, you form a black hole that you essentially form a black hole, and what we have to assume is that still significant amount of matter still ends up outside the horizon during this collapse process, so that you can actually have something like an accretion disk that accretes onto the black hole and forms a jet. Now there's work by Ben, who's here in the audience, and Brian and others who have actually shown that this is actually fairly unlikely to happen. So we're not really sure if say uniformly rotating, or say more or less uniformly rotating neutron star of that kind can actually produce a black hole torus system when it collapses. But this is something that we should also further investigate with also the simulations.
Okay. So it might not even necessarily be would it necessarily be a short GRB?
Well, in this case, yes, probably, because the typical timescales for accretion of such a torus would be on the short GRB.
So if you did make a torus, it probably would be
Yes.
short GRB, but it may be really hard to make a torus
Yes.
from a solid body neutron stuff.
Okay, before we are standing between the wine and people, we should talk about everything. So Kota, why don't you go ahead?
Yeah, actually, it's around the same line. So this is a kind of the configuration for it's a case called a supernovae, and then actually Brian, people actually try to explain the connection between the superluminous supernovae and GRB and perhaps HRB using the parser. And then the scenario that follows, so that if you put the parser, the pointing flux is dissipated for the non-summer radiation, and then the ejected non-summer radiation, fraction non-summer radiation is converted to summer radiation, and then it's ejected sick, and then you can use or shock, and then you can expect that the significant summer emission from the parser-driven supernovae, and then. But if you wait for a long time, eventually the ejector starts to, be seen. And in this kind of scenario, I think that it's quite natural to expect that no summer emission, because this is assumption is as follows. Of course, at the earlier stage, we are not sure how the magnetic dispersions go, right? But if you look at the galactic parts of wind nebula, and then we know that the most of the pointing energy is dissipated for the northern partners. Let's take this assumption, and then if you extrapolate this physics to the early phase, and then it's natural to see expect the northern signatures. And then just by adopting this assumption, you can calculate the northern signals, and just you can predict actually by fitting the supernova light curve. And then you can determine the parameter space and the spin down time as the period, the magnitude, and the ejector mass. And then you can try to calculate the radius and the X-ray emission. I think that usually the X-ray emission is very strong, but also affected by the absorption in the ejector. And I would like to point out that the radio emissions can also be interesting. And because if you wait for the couple of years, 1 year or 10 years, and eventually the system becomes transparent for the free absorption or singular absorption, and then for the nearby supernova or nearby superluminous supernovae, then it's start to be possible to see some characteristic radio signals from these kind of nebula. And this is I think that this is especially powerful at higher frequencies, such as the sub-megahertz frequencies, because you can avoid a free absorption. And then, for example, if you make a follow-up observation with Varma, then it's possible to see the radio signature. There is
What do you mean by GW effect?
Oh, this is I'm talking about later. Then actually, this is one slide. This is actually Brian mentions that in principle in the early phase, and then here another assumption is that that I basically try to explain this superluminous supernova, several these stripped envelope supernova using the spin down power of parser. But in principle, for example, there are many possibilities. But if, for example, if the internal field, toroidal field is so strong, and the neutron state is distorted, and you can achieve the situation where the gravitational wave loss, energy loss dominates in the early phase. And in this case, actually, of course, your spin down power is reduced, and the optical radiation is suppressed, and the later emission is also suppressed. And in this case, it's good for the gravitational wave detection, but actually, you have the anti-correlation between the electromagnetic signature and the gravitational waves, of course. And then I just demonstrated this, and then if you ignore the effects of such gravitational waves, and it's actually easy to find the parameter space to explain the superluminous supernovae using the spin down timer. But if you put the strong magnetic field, for example, if the distortion parameter is around 10⁻⁻3, and then or Q times 10⁻⁻3, and then early magnetic gravitational wave loss start to be important, and then it's very hard to find a parameter space to by which you can explain supernova.
But it is not good news for the gravitational wave, because these are not gravitational waves that can be measured. The time delay, the time scale of this gravitational wave emission is much longer than, so the luminosity is much longer, so it's bad news for everybody.
It's bad news for everybody. But it depends on this parameter, right? If you put the strong weight actually.
Yeah, if you put epsilon to 0.1, then you will get some.
Yes.
But with 10 to the minus 3, you will not get the detectable gravitational wave signal.
But you have to be, of course, even the 3 times 10 to the minus 3, you need to see the signal very nearby. I think the only Virgo, you need to put a Virgo, yeah.
For the most optimistic one, what would be the reflection rate?
Well, if you consider supernova, no. So that basically, it's very bright future for us. But it depends, right? Because in general, if you take if such a thing happens in the usual quantum supernova type 2, I can exclude such a possibility. You expect one or few years, right? It's Virgo.
Yeah. Okay. Yeah. Very good. Very good. Thank you. I think let's move on. David, you want to add something? What was not mentioned that is interesting?
I can say a few things. I was asked to answer the question whether observations can help simulations or the other way around, which is a very nice question. I think, the goal of observation should be to help simulations for sure. Because of course, simulation should be a tool towards understanding the observations. More seriously, there are things that actually will make our lives as simulators easier if we learn them from observations. For example, if we can rule out the presence of other physical effects, for example, like nonlinear tides in the inspiral, the impact of, for example, a Poynting flux rebrightening the ejecta in the modeling of Kinova. These are kind of things that are very difficult to model in simulations, where we might actually get a handle on already from the observations using simple models. So this is one part of the answer that I would give to this question. The dual answer is what needs to be done in simulations now in order to help observations. I think there are two important things that simulations should do and will do in the next few years. One is modeling the post-merger emission of gravitational waves better. It's something that we have discussed a little bit before. I think that we're still a long way before we have gravitational wave signal we can trust to the phase level accuracy. So we cannot really do much filtering with what we have now. And the other thing that we should try to understand using simulations is whether all binary neutron star mergers make a short gamma ray burst, which is also something that has been discussed this morning. And here I think one interesting thing that we have to ask ourselves is if only a fraction of neutron star mergers make a short gamma ray burst, what is special about them? And can we, by looking at simulation results, can we identify if there are families of solutions? For example, I don't know, if for some equation of state 20% of binaries make short-lived remnant. We know from observations that only 20% of binaries should make gamma ray burst. What does this tell us? So this is, I think, the kind of questions that we have to address with simulations. But more in general, I would be happy to hear what you as a community want our simulators to compute.
So the question that you meant, so there is a degeneracy between, so this is something I didn't know. I thought either you produce or you don't produce electromagnetic observations. You're now saying, okay, there may be a fraction of these binary neutron star mergers that don't produce anything. But then that is degenerating with the angle. You don't know whether you're not observing it because they don't emit or because, are you talking about the EM afterglow or are you talking about
I mean, we have always assumed that if you merge two neutron stars, you always make a gamma ray burst, but I don't think this has to be necessary.
So that, if that is the case, then I think that is completely degenerate with the beaming angle.
That is true. This is why we need better simulations.
So I would say that is very
fraction of neutron stars are peculiar, for example.
Yeah, it would be very helpful to understand that problem.
Just one thing, you say that if you, for example, are in ongoing observation, which then you can go and simplify or tweak your code, you reduce what you're observing. I think that would be very dangerous because you have one sample out of a big parameter space.
Yes.
And if based on those you make some physics that you may find later on. So I don't think that would be a good approach. I think
Yes,
something that
I'm not arguing towards simplifying the simulations or tuning the simulations to reproduce observations. But there are things that we worry about when we do our simulations that are currently not under our control. For example, it has been proposed that during the inspiral you can have nonlinear tides, and this will have this will excite very high frequency modes inside of the neutron star, something that has hundreds of radial modes. This is something we will never be able to resolve in simulations. This is something that I have to somehow include as a subgrid model, or I can just pretend this is not a problem. I mean, this is something that observations can answer for us.
Why can't you do it in simulation? Why don't you see it in simulation?
Because in order to resolve this, we would have to have a resolution of thousands of grid points across the star, which is currently orders of magnitude higher than what I can afford.
Is it that we can never do it, or it's just that it would require a gargantuan allocation?
Might be possible, but we would have to design specially designed codes that are able to simulate these nonlinear tides to high order accuracy for long time scales. And my impression is that before we're able to do that, LIGO will tell us whether these nonlinear tides are there or not. In this sense, I say that observations can help simulation.
I mean, the GR code would be total overkill for this. You just take a star and try to excite it.
You will have to design a special code to do this. A general purpose code like mine cannot do these simulations.
I mean,
because I will need to resolve to evolve the binary for many orbits at very low frequency with very good spatial resolution.
Given that this might completely invalidate, our templates, I think it's a big enough question that I wish someone would try to make that special purpose code and just do the simulation.
Yes, this is one way to look at it. My way is I cannot do this problem before LIGO detects binary neutron stars because I'm very optimistic and I think that you will detect binary neutron stars very soon. So
that's just saying that you don't think that this effect is real, though.
I think like a major thing observationally that would really limit the possibilities is if, I mean, this is not something this room necessarily works on, but like when the more mass, when the the two smaller mass neutron stars were discovered, and suddenly this whole class of equations of state were thrown out.
Yes.
I mean, that really changed people's view of what the outcomes of mergers could be. So I think in the same way, if you discovered a 2.2 and 2.3 smaller mass neutron star,
yes.
Then you could really reduce the subset
of course, if we have a reduced set of equation of state, we can
or with
cover
whatever
boundary
radii,
space better.
whatever.
If we have knowledge that the magnetic fields are small for binaries that are merging because these are all binaries, then we can also neglect magnetic fields in our simulations and things like that. Of course, ideally we would want to include everything. There is a limited amount of resources we have.
Such a one last point before, because
yeah, I was just going to say that this might be a chicken and egg problem because unless we know that there are these nonlinear tides, we may not be able to detect them.
Yeah. Well, we can
parameterize that there is a problem.
No,
it depends on the extent of that effect.
You will see that
hopefully it's not so bad.
You will see that you get waveforms that don't fit the simulations.
We need match filtering to be able to actually get those signals.
If you tell me that the waveform template are so large that you will fit anything that you will see, then
no, not with
this is not serious.
Binary neutron stars, you don't pick up. I mean, binary neutron stars, you absolutely need the pick them up.
No, but the question is whether the current matrix of templates is so large that if this phenomena exists, you will not notice it, you will just identify that this was a merger with different parameters, then the whole exercise is getting nowhere.
It may be, but the question, we don't, if people can tell us how it affects the field, and that it is not completely orthogonal to our bank of templates, then it's fine. At the moment, we get the picture that some people say it may be so bad that you won't even capture it with all your bank of templates. you're still not going to do it because this waveform is orthogonal to.
Oh, so you expect that you'll not detect it at all because the
Yeah.
template is
Yeah.
But
I mean, that's what some people claim. I don't think it's.
So there are people who are working on building parameterized templates that include a knob that you can turn to mop up these events. But that comes at some cost in our horizon distance. And so, I mean, this model uncertainty is, has, I mean, you could think of it as it has a dollar cost equivalent to, an upgrade of LIGO that, increases your sensitivity by 1 over that factor. So it's, I mean,
But one way to get a handle on it would be if we knew at what frequency this effect became important. Like if it turns on at 800 hertz, probably not a big deal. If it turns on at 250 hertz, then it will really mess up the sensitivity of the.
Yes, actually, I'm not advocating for this effect.
See what you created without advocating.
But this is the way to be a hero and say it's not going to matter without having to spend a lot of computing time. If you can say that it
I
doesn't,
can
it
say
doesn't
that
matter
it's
below
impossible
800
to
hertz.
simulate, so it's not my problem.
Yeah, so this one is contributes from low frequency and accumulate to high frequency.
The nonlinear tides?
Yeah, this is expected to happen at 40 or 50 hertz.
oh, forget it, we're screwed.
No, we can do 100 hertz off. That's the point, right?
Oh.
You can essentially get 100 hertz.
So we should forward integrate as well as backward integrate
Well,
and see where.
Just start at 100 hertz. We used to do 100 hertz. Don't you remember
that's
this one?
That's correct.
Tony, sorry, you wanted to
So,
add something?
I'm sorry, I'm confused. So, maybe this is a question for Brian, Steve. I'm confused by the title of this session. So, my question is, what's the difference between joint observing, co-observing, and follow-up? What have we just been talking about?
I'll let the panel answer this.
Okay.
Please.
I have the slides.
Oh, this is the previous one, right?
Yeah, but-
Okay. Yes, let me.
Well, you'll pull up the slide, but basically we are comparing two scenarios. One is we have the EM counterpart, we detect the EM counterpart. Second is we don't have an EM counterpart for whatever the reason. I think for LST we can do both. We can do EM counterpart, and also you mentioned before we are going to have a quite complete gassy catalog, and by gassy association we can also do cosmology or astrophysics. And I just did some calculation, only focus on cosmology, so H0 measurement, and comparing EM counterpart case to no EM counterpart case, and we got 40% better uncertainty. So you will reduce your uncertainty on H0 measurement by having an EM counterpart. That's
Now
the
I'm
number.
even more confused. So,
Yes.
does this mean that we have to follow up? This presumes that we follow up a gravitational wave event and find or don't find something? Or are you talking about the fact that we will cover, let's see, twice a week we will cover every piece of the sky in some filter, and therefore there will be automatic monitoring, and you're calling that joint?
What do you get for free from the survey, and what do you have to spend more observing of?
Well, that depends entirely on the survey, but
It,
we have the particular survey.
it
We
is-
fixed the survey.
it is
I'll
a
see.
Well, but
different
it
question.
doesn't. It all depends on timescale, right? I mean,
It depends on both this.
right, but he's
the
described
timescale.
the survey.
Yes.
Right,
depends
given the
also-
survey that was described, what
It
you
also
get for free,
depends.
and what would you have to get with the TOO?
It also depends on what kind of EM counterpart you're talking about. If you're talking about X-rays, gamma rays, then the situation becomes much easier because it comes with the location, so it narrows down where
So this is
to
not
look.
co-observing. We're not talking
No,
about
this is
co-observing.
not co-observing.
This is
We
joint
don't
observing,
know.
which means
Yes.
that we're both on the air during the same year.
Now the thing is, if you have X-ray monitors, which are all sky except for, of course, with the rotation by the Earth, then you probably will cover everything that you guys can see, depending on the time of the day. But if you don't have an X-ray counterpart, then you depend on after the effect. You look and see if you can find the, now in this case, the optical infrared
So that's
follow-up.
That's follow-up. But the title of this was joint. That is confusing me. So we're talking about statistics here, just a statistical cross-correlation, not an object-by-object, right?
So the goal of the panel was to discuss all these possibilities. Basically, if we do whatever we need to get more science out of LSST observations and LIGO observations in whatever combination, what are we learning, right? We're not doing this to count a number, like how many detections we make with both. It's really about learning physics,
So it
astronomy,
seems in that
etc.
sense it would be very helpful if we had more than 2 visits to every place in the sky per week.
Depends on the source, I guess.
I think we have 2 or 3 anyway, so maybe that's enough.
Yeah.
I mean, yeah, part of this is we have a LIGO air region, and the question is how many visits do we need to identify whatever predictions we make for the counterparts versus all the background sources? And also how many candidates is an acceptable number to reduce it to? If we can pass off 100 candidates or we pass off 10, I mean, so these are sort of things that will come into this.
Yeah. So, well, then we are going backward here. It's just a summary for all the localization in 2D, which is more helpful for EM counterpart. So this is just a number taken away, assuming BNS rate of the middle number, the 10 to the minus 6 per year per cubic megaparsec. And apparently we are going to get many for HOV or HOV-JI, so 5 detector case. We're going to get, this is a number of detection. So basically very high fraction of it. Those number are the total number of detection. Well, like 7 or 80 out of 83, so basically all of them is going to be very well localized. So
what's the shape? Is it a blob or is it more like a
it's
banana?
just like,
just a blob, okay.
yeah.
So that's one
so
direction.
this is just one scenario for specific for follow up the EM counterpart. Well, if you can go to next slide. This scenario is a 3D case, which is more helpful for this galaxy correlation. So if we have this galaxy catalog, we don't need to do it real time. Basically, we can do it afterward. So this case, well, we can still have a few, but not that many, bi-neutron stars that are well localized, and you can identify the galaxy.
So you mean that the galaxy catalog, you have the galaxy catalog up to the,
Suppose we have a galaxy catalog.
Yeah.
Out of this, say, 80 detection, you're going to have 10 of them will be well localized down to this number. So 1,000
you have mentioned some concrete up to very high.
No, you don't. So that's actually a point of this well-localized event, because this well-localized event, one reason they are well-localized because they are super nearby. So all of them are gonna be less than 100, 200 megaparsec, which can be very easily done by LST, for example. So we don't really need something that's very far away and very complete. Like, and this also applies not only for bi-neutron star, the galaxy catalog approach, we've been talking about this because we want to do it for bi-neutron black holes as well. And for those bi-neutron black holes, we already detect those 30-30 solar mass one. Yes, we can see them very far away, but still, for those very well localized ones, they're still lying within redshift 0.1 or something. So we said for galaxy catalog within 100, 200, well, as far as say 400 megaparsec, we can do all the things we want to do with this galaxy correlation.
So, and you can do this. You don't have to already have the galaxy catalog. You can, since at this point maybe you've given up on actually finding a counterpart. That's done, and so you can take as long as you want to do, a deep, targeted survey. And then go back and inspect.
But it doesn't take that long to do it. So
yeah, it's
no,
just
right,
but it doesn't take long.
Yeah, but it doesn't have to be done right away.
Yeah, real-time galaxy catalog, or just you can do it either way.
So I don't understand the logic. So just calculated the 17,000 galaxies per square degree at redshift 0.1.
Yes. But the
How does that tell me what galaxy did this? I don't understand.
So the event itself is gonna be very well localized down to like say 100 cubic megaparsec or 1,000 cubic megaparsec.
Lots of galaxies inside that.
If you multiply by, well, it depends on the galaxy density you are assuming, and also depends on your survey depths.
Yeah, well, we know what our survey depth is, and we know what the galaxy density is at redshift 0.1 very well.
So what will be the number?
17,000 galaxies in 1 square degree to redshift 0.1, which is in that volume. So this is too many galaxies.
To what completeness?
Yes.
100%. We will be 100%
So
complete at redshift 0.1.
So we did, the typical number we were taking here is like 0.01 galaxy per cubic megaparsec. And if that number is something that you can consider as like complete, then you just multiply this number, you take 2 digits off, then that's the total number of galaxies within this volume. So that is not that many, it's like order of a few galaxies. So those are, those because you only have a few, then those are gonna be very helpful, and actually most of your fit is gonna come in from this golden event, because once you got an order of magnitude larger volume, you got an order of magnitude more galaxies, then everything wash out, no information at all. So no matter what, golden event is something you should just, if you have limited resources, you should just focus on them, because this is where you're gonna get most from.
But I guess the point is, it's not, I mean, you're never going to see all the, there might be some little tiny galaxies you never see, but it's just that we expect, you know, most of them to happen in L-star galaxies. So we're really sort of mostly caring about the L-star galaxy density.
Yes, yes.
And not sort of the total. I mean, we don't, if they all happened in dwarfs, we'd be really in trouble with this number. So if they all happened in tiny galaxies.
Okay. If you can, do you want to add something?
Yeah. So I was asked to comment on how well we, or how, how much improvement we gain in terms of joint observations in probing nuclear physics compared to like gravitational wave observation alone. And I could see 2 possibilities at least. One is to use the relation between tidal deformability and the intrinsic mass of a neutron star. So just like mass radius relation depends strongly on which equation state you keep, this relation between tidal left or tidal deformability and the intrinsic neutron star mass depends strongly on the underlying nuclear physics. So any independent measurements of these 2 quantities allow us to probe nuclear physics. And we expect to measure the tidal deformability and also the redshifted mass by using gravitational wave observations. So if we have electromagnetic counterparts, and if we can identify host galaxy, and if redshift information is available, then we can break degeneracy between redshift and redshifted mass so that we can extract intrinsic mass information so that we can probe nuclear physics. That's one possibility. Another possibility is to use the amplitude information of post-marginal signal that David was mentioning this morning. This amplitude has interesting information about nuclear physics, and if we can localize the host galaxy or the gravitational wave sources, then we can include this information into the prior when we do gravitational wave data analysis, so we have a better measurement of the amplitude. But for this case, I'm not sure if we can get the inclination and also polarization angle that also enter in the amplitude. So maybe there's some degeneracy between these extreme parameters and also the amplitude that we want. So this approach might be more tricky compared to the first analysis. And if you have other ideas, then I'd be happy to hear. But yeah, that's it.
People are thirsty, maybe? Okay. Thank you very much. Thank you for the panel. So I guess we are ready for the wine and refreshments. So thank you for staying so long.
One word of caution. So there are some people who love sweet wines and some people who hate sweet wines. So there is one bottle of Porto. So please take a look.